On the 20th day of July in 1969, at about 10:05 p.m. Milan time, Apollo 11 lit its descent engine for its descent to the lunar surface. Apollo was the first time that men entrusted their lives to a digital computer, in other words, to code. The mission required it, and now the mission has reached its most complex and dangerous phase. On the Lunar Module, Neil Armstrong and his co-pilot Buzz Aldrin were cleared to proceed. In Cambridge, at the Massachusetts Institute of Technology, we clustered around a squawk box that linked us to mission control and let us hear the conversation between Houston and the spacecraft. No one knew at that moment that when the LEM systems were powered up, a condition was created which stole 13.4% of the computer's CPU time. That time was consumed in counting meaningless pulses. When the lunar landing guidance equation was engaged 26 seconds after ignition, our margin dropped down to around 16%. A little later, when the landing radar began to acquire data from the lunar surface, our margin dropped to around 14%. And when Buzz Aldrin keyed into the computer a request to look at the landing radar data, our margin dropped by another couple of percent, and we were in deficit. What happened next, with the whole world watching, and it happened 4 more times before the LEM planted its feet in the lunar dust of the Sea of Tranquility, was the moment when code, the music of the machine, became an actor in human history. There are many places to begin the story. I'll started right here in 1922 when Charles Stark Draper, popularly known as Doc Draper, traveled with an undergraduate degree from Stanford, traveled across the country to MIT. At MIT, he found just the environment that suited him. The MIT motto is mens et manus, mind and hand, and that fit him like a glove. At MIT, he compiled the longest transcript anyone had up to that point, and he became head of the Department of Aeronautics and Astronautics. In fact, the department name was changed from Aeronautics to Aeronautics and Astronautics during his tenure. One of his early triumphs, or not that early, I'm talking about the era of the Second World War, was to use his technology of gyros and accelerometers to create a gun sight that made it possible to defend surface vessels against air attack, which was very successful. After the war, he and his lab began to study the more general problem of three-dimensional navigation, inertial navigation. This in 1953 is the installation of the first practical 3D navigation system in MIT's B-29 aircraft. You can see roughly how big it is. That aircraft flew across the country to a conference in California on the subject of self-contained guidance systems. And after listening to a number of speakers talk about the difficulties of doing it, Doc Draper stood up and sprung his trap. He said, well, I just did it. After the flight controlled automatically from Boston to LA, the position error was about 8 miles. There's another story told about Doc Draper some years later, which is that he was interviewed. This is after MIT got the contract for the Apollo guidance system. He went to a meeting with Jim Webb, the head of NASA, and a little dialogue took place. Jim Webb said, "Can you build a system that'll take men safely to the moon and back?" Doc Draper simply said yes. This happened in the living room of Jim Webb's home in Georgetown. Jim Webb said, well, when will it be ready? Doc Draper replied, it'll be ready when you need it, Mr. Webb. Webb then said, how do I know it'll work? Doc Draper said, well, I'll go along and operate it. He was about 60 at that point. He wore glasses. He had scrubbed out of flight school some years before. But he did write a letter to NASA seriously arguing that he should go along. Of course, that did not happen. But it's one of those stories that sort of created an image of Doc for those of us who, a number of levels down, were working for him. And then things went too far. Things became more dramatic in 1957 when Russia orbited the Sputnik spacecraft. And at that point, the lab started thinking much more seriously about interplanetary type missions. And in 1961, in that same year, Yuri Gagarin made his first manned flight. That was followed by Alan Shepard's 15-minute suborbital flight. And emboldened by that, on May 25th, John Kennedy announced the plan to go to the moon and bring the men back by the end of the decade. And very soon after that, MIT got the contract for that primary guidance system for both Apollo spacecraft. And one of the early things that needed to be found out was whether the combination of human skills and optics were sufficient to do the job. And this rig was constructed. It was on the roof of the building that I worked in. And that's the smiling Doc Draper at the controls. In the left picture, going back to 1955, that's the second version of the system in the B-29. Doc Draper is explaining it to the reporter, Eric Severide. By the time we got to Apollo, the size of that inertial sensor was down to about a 1-foot diameter. That's in the right-hand picture. You can see that lumpy assembly at the middle, which consists of 3 gyros and 3 accelerometers. And the gimbals that surround that are designed in such a way that that inertial platform at the center, as we called it, it was also called the stable member, that could be held in its inertial orientation no matter how the spacecraft operated around it, moved around it. That gave us the attitude reference. And since there were also accelerometers there, it gave us the ability to measure the thrust during a powered flight operation. I came into the picture only 3 years before Apollo 11, in 1966. I was hired by George Cherry in the upper left. He was a very shy man. That was the only picture of him we were able to find. He was the project manager for the onboard software for the Lunar Module, and I was assigned to work with Alan Klump, who was on the analysis side in charge of the lunar landing. That is the guidance for that last 12, 13 minutes from lunar orbit down to the surface. That's the nondescript building we worked in. And that little picture at the lower right is a baby-faced me at the time I was hired. That's my badge photo. Working with Alan, I would eventually program the lunar landing guidance equation, the surprisingly complex throttle control algorithm, and a number of other pieces of software, most of the onboard code that was specific to the lunar landing. The tools were there. We had an assembler that allowed us to add our code to the accumulating program for a given mission, created by Hugh Blair-Smith. We had various simulators that allowed us to test that code. We even had a Lunar Module cockpit, which is what's in that picture, that let us play pilot when we were testing a phase of the mission where pilot inputs were important. And we even had that tool. That's a key punch machine. The place where our hands touched the clay, so to speak, was sitting in a machine like that. I don't think too many people in this room have used an IBM key punch machine, but it became second nature. And we also had the innovative operating system for the onboard computer that was conceived by this man, Hal Lanning, one of the true unsung heroes of computer science, worthy to be considered in the same breath as Grace Hopper, for example. He did a number of things in his career. He created the first algebraic compiler in the early 50s, but he also conceived of this operating system for the onboard computer, which could allow us as programmers to schedule two types of entity, something we call tasks as a technical term, which for small pieces of code that could be made to operate at exactly the time we wanted them, and jobs, which could be of any length. They carried a priority, and higher priority jobs could interrupt lower priority jobs. This system allowed us to make use of the meager computational resources that we had. There were also two languages that, if you can read it, are illustrated on this page. About halfway down, we transitioned from the assembly language, the machine language, if you will, that we called BASIC, no relation to any other language called BASIC, which was fast, relatively speaking, but not so compact. But we also had a language we called interpretive that was implemented by a series of subroutines that were actually in the onboard code. We called it interpretive, and that gave us a much more compact but also much slower way to do the vector matrix operations that were part and parcel of navigating in three-dimensional space. And using those languages, we built up these programs. That book, which is 6 inches or thereabouts thick, over 1,000 pages, holds the entire code for a given mission. Also in that picture is a coding form, a loosely stapled memo, which was our language manual. Coca-Cola was my own fuel when I was doing this work, and that button that you can't very distinctly see comes from an anti-war demonstration that some of us attended. These programs evolved, of course. There was a program called Sunburst that flew the LIM 1 mission. That was an unmanned LIM mission. Not very successful. In January of 1968, that led into a program called Sundance, which flew only one mission. That was Apollo 9, the Earth orbit mission with both a command module and a lunar module. And that in turn progressed into Luminary. And Luminary, in a number of different revisions as it evolved, flew all the lunar landings, all the lunar landing missions in the Lunar Module. That code was packaged in modules. I have one here. This is 12 kilobytes of extremely reliable read-only memory. A number of these modules survive and have been scanned, and they've all been found to be perfect. It's a form of memory called core rope, in which a 1 is implemented by a wire that passes through a magnetic core, I should say a ferrous core, and a 0 by a wire that passes around it. To read a given word of the fixed memory, certain cores were activated and certain sense lines were read. And between those two things, the computer was able to read the 1s and 0s. The computer weighed 32 kilograms approximately. It consumed about 55 watts. It takes up about 28,000 cubic centimeters of volume in the spacecraft. The word length was 16 bits. One of those bits was devoted to parity checking, and of course there was a signed bit, so the precision of a single word of memory was 14 bits. We also had the ability to do certain double precision operations. The total memory was 38K words. Of course, that corresponds to 76 kilobytes. Of that, all but 2K words, or 4 kilobytes, was this read-only memory that I talked about. And so the memory that we had available for dynamic results was 2,000 words, or 4,000 bytes, which of course had to be used very efficiently. And those locations were time shared, sometimes as deep as 6 deep. And it was a big job to make sure that 2 programs using the same memory didn't run at the same time. That was one of the integration headaches that had to be dealt with. Another interesting thing about this computer was that it used integrated circuits. It may not surprise anyone here, but in the early 1960s, that was a daring decision. Integrated circuits existed, they had been developed, but they were not very reliable. And the work that was done at MIT and in conjunction with industry went a long way to demonstrating the reliability of integrated circuits. That circuit there shows you what each of those chips had in them, only 6 transistors. There were 2,800 of those chips. The total transistor count of the whole machine was therefore something under 20,000. Now, the picture of the computer a couple of slides ago showed you the DISKI, the display and keyboard unit. This is a closer up picture of it. The capability we had for general purpose information was 3 5-digit registers with a sign. There were some other special purpose instruments also driven by the computer, but this was our flexible way of doing it. And you notice the 2-digit verb and the 2-digit noun. That was our language of verbs and nouns that was used in both directions for communication between the man and the computer. That was thought of by a man named Ramon Alonso. And there was also the current program that was in operation. P63, P64, and P66 were the main programs for the lunar landing. And also in that display are some special lights that were used in various ways differently in the command module and the LEM. But one of those lights that was in common between those two was the program alarm light, labeled PROG in that. Okay, why did we need a computer? Well, the computer did guidance, navigation, and control. Control meant managing the attitude or orientation of the spacecraft in response to commands from the guidance or commands from the crew using their hand controller. Navigation meant integrating the information from the inertial sensor that I showed you before, from optical sightings on stars and horizons, and in some mission phases, information from radars in order to always keep track of the position, orientation, and velocity of the spacecraft, which we called collectively the state of the spacecraft. Interestingly enough, one of the requirements for the Apollo primary system was that it be able to do these things autonomously. As a matter of fact, from scratch, using sightings on planetary horizons and stars, the primary guidance system could figure out its state without any help from the ground. In fact, the only thing that required, as missions were flown, the ground was always double checking what the onboard system was doing, but the mission still could have been flown without that, except for being able to land accurately at a given spot on the moon. And finally, there is guidance, the discipline called guidance, which means using the navigational information, comparing that to a set of targets, and firing an engine in such a way as to achieve a given orbit or a transfer trajectory, or to land or take off from a body such as the moon. Now, the lunar landing was divided into a number of phases. They corresponded to the programs P63, P64, and P66. The first phase, the longest, was known as the braking phase. It began at the low point in a lunar orbit of around 50,000 feet, about 9 miles. And by the way, I should say that we tended to think of altitude in feet, even though the computations in the computer were taking place in metric. And that was because the pilots, the astronauts, preferred that, and it always seemed more natural to talk in terms of the altitude as feet. So you'll hear me talking about feet as well as meters. At any rate, it began at about 50,000 or 49,000 feet, with the spacecraft going at about 5,500 feet per second, divide by 1/3 to get the meters per second, and on the order of 250 nautical miles shy of the actual landing site. Two things happened during the braking phase that were important. One of them was for the landing radar to lock onto the surface. The other one had to do with the throttle operation, and I will talk about that a little more later. The braking phase led to the visibility phase, which only lasted about 100 seconds, 105 seconds. And during that phase, the LEM was in an attitude where the astronauts, looking through the LEM's windows, which were big for a spacecraft, could see the surface in front of them, and they had the ability to shift the landing site that they were going to as necessary. And finally, at around 400 or 500 feet, by design, the astronauts would, when they wanted to, switch to a semi-manual mode called P66, in which, flying somewhat like a helicopter, they were able to choose the precise spot where there were no rocks or deep craters to let the LEM land. That picture is a picture of the operation in the cockpit during the visibility phase. The LEM pilot on the right, that would be Buzz Aldrin, whose LEM pilot is a misnomer. His main job was computer operator. The real pilot was the commander, Neil Armstrong. At any rate, the LEM pilot would read an angle which was displayed on the disky, that 43 in that illustration, which told the commander, Armstrong, where to look along a scale in the left window to see the spot where the LEM would land if he took no further action. The end conditions that the lunar landing guidance equation had to satisfy were fairly complex. It had to meet targets defined in position. It needed to land at a suitable spot in the Sea of Tranquility. Velocity, it had to be moving very slow, on the order of 1 meter per second by the time it landed. And it needed to meet terminal conditions and acceleration too, because it needed to be upright when it got there. Another thing that had to be managed during the lunar landing was the control of the throttle. The LEM's engine was throttleable, which in those days was unique. As a matter of fact, there's still not many rocket engines that are deeply throttleable, that will throttle all the way from their maximum thrust down to a low value. But one of the constraints was that we were not allowed to operate the engine in the region between about 60% and maximum. And so it was not until that point in the braking phase called throttle down that we actually had full control of the throttle. When you think about it, it's impossible to hover without a throttleable engine. And all of this going on in the computer at the same time, along with some background activities, was quite time-consuming, much more so than any other phase of the mission. And that's illustrated by this plot of the duty cycle. You see that the highest point towards the right of that curve, our margin is less than 10%. That's during the visibility phase. Excuse me. Oops. That's the crew, Neil in the middle, Buzz Aldrin on the right. The guy on the left is Mike Collins, who is the one who stayed in the command module. Ironically, Aldrin was a rendezvous specialist. His mission had been with Jim Lovell on Gemini 12. Neil had flown with Dave Scott on Gemini 8. And as some of you may know, they had a problem with a stuck thruster that was gradually spinning the spacecraft up. And they were able, fortunately, before they blacked out from the spin rate, they were able to bring that to a stop, but at a cost of having to come back to Earth immediately, which they did. So you could say that Neil Armstrong's only mission before Apollo 11 was an abort. But to show what a cool customer Armstrong was, one of the stories told about him was that one early one morning, he was flying this contraption called the Lunar Landing Training Vehicle, which was a flying machine on a reaction engine that controlled its attitude with thrusters. And however, it was extremely difficult to fly, especially in an atmosphere when there might be wind. And Neil did get in trouble flying it one day and had to punch out. You can see in the lower right picture, it fortunately had a very capable ejection seat. You can see Neil hanging from the parachute. The interesting thing about this story is that, told by another astronaut, is that somebody said to him, "Did you hear Neil had to eject from the lunar LLTV this morning?" And they said, "No, that couldn't be. He's in his office working." In other words, despite that experience, he went straight back to work and was in his office that afternoon as though not much had happened. Now, I mentioned the fact that a condition had been created that had stolen over 13% of the duty cycle. I'm not going to really go through this, but the problem was that with the setting of the switches on the control panel, which had been a hasty last-minute change that perhaps hadn't been fully thought through, that angle resolver at the lower left was being fed by contradictory information. And it's that created this storm, if you will, of angle pulses going to the computer, enough to consume that 13%, because the computer had to count those pulses itself. And after the radar had locked on during the braking phase, Buzz Aldrin had keyed in verb 16, noun 68, using that verb-noun language, in order to look at radar data. That third number in the display, that 2,900, that's in feet, that was the difference between the altitude as derived from the radar data and the altitude from the inertial system. That was a figure of merit to decide whether or not to accept the landing radar data. But when Aldrin did that, that added a couple of percent to our duty cycle, and that caused the first of the alarms, a 1202 alarm. And as soon as following the ringing of the alarm tone and the lighting up of the program alarm light, Aldrin keyed in verb 5, noun 9 to see the alarm code, and that's what it looked like. No simulation modeled the effect of the time loss as a result of that interface. Very few people had even seen it, because it could only be seen if you were working with the exact flight guidance system. It had been seen by a couple of people, but they hadn't raised enough of a stink, so the problem was not widely known to people like me who, as a matter of fact, as we realized later, it could have been fixed, or the hazard could have been avoided with 5 lines of code if we had only known. The result of this was, and my order may not be right, because of our time deficit, more jobs were being scheduled than were being completed. The right-hand example shows that, because the job called servicer, which was the big 500-pound gorilla of the work that was going on in the computer, because that was unable to finish, it held on to its space in the queues. And when the queues became choked with data, there was no room to schedule a new job. As a last resort, the operating system would, in fact, command an alarm. That was a system that was put in place, this ability to, and as a result of that alarm, we did a restart, a reboot on the fly. That system had been incorporated into the software to deal with power transients, the likelihood that there might be a flicker in the LIMS pilot. So synergistically, it was used by the operating system when it really didn't know what else to do. And when that process of the queue space being used up is shown on the right here. And when the alarm occurred, those queues were flushed and we started over. You can see that in the right-hand picture. But cool heads in Houston and on the spacecraft prevailed, and we were able to land successfully. One small step for a man, one giant leap for code. It was the dramatic debut of software on the world stage of human history. No longer was code data processing. No longer was it an invisible machine part. Now it was an actor. When the problem occurred, it acted quite visibly so that the operation continued, and the operation in question was a lunar landing. The history of code in the years since has not been all triumphant. Code has been a factor in wrecks and airplane crashes. We saw that very recently with the 737 MAX. It was probably an advantage that there were only something on the order of 30,000 lines of code in the LIMS computer. You saw earlier the book that it would all fit in. That meant that you could find the solution in that one book if you could puzzle it out, which was not always easy, but at least you knew the answer was there. Now, in the period after Apollo 11, the software continued to evolve. The goal set for the very next mission was to land precisely, and the target was a surveyor spacecraft that had landed several years before. On Apollo 11, Neil and Buzz had landed about 4 miles away from the point where they were designed to land. Of course, it was still a triumph. It was the moon. I had a brief conversation with Armstrong in the hallway during a training meeting a few months before that. He had said he didn't want to use the capability to shift the landing site during the visibility phase, except maybe once to show us it worked, he said. And I urged him, if he saw something interesting, to fly there using this system. He said, well, any spot I can land on the moon will be interesting. The Apollo 12 was successful. That marked the period when I started going to Cape Canaveral and using, instead of our plywood cockpit in Cambridge, using NASA's very sophisticated Lunar Module mission simulator, which you see there in green. The brown in the background is a command module simulator. Inside that irregular cluster of boxes in the foreground, the astronaut John Young called it the Great Train Wreck, is a LIM cockpit. Those boxes are there to provide the visuals for the windows. And that simulator was very good. Before the end of the program, I flew dozens, probably hundreds of landings in that on a few occasions with an Apollo astronaut, an Apollo mission commander, and many times on my own, because it was useful in some ways for software development. We did a number of other things. For Apollo 13, although it was not used because of the problem on that mission, we had greatly simplified the semi-manual phase at the end of the landing to help the astronauts cope with the dust that was kicked up by the engine that made it hard for them to judge the LIMS attitude and its horizontal speed across the surface. We also put in a terrain model that made it possible for Apollo 14 and the later missions to land in lunar terrain that was not as even, was not as flat as in the Apollo 11 and 12. And the program continued to evolve. through Luminary Revision 210. Luminary 99 flew Apollo 11. Luminary 210, as it further evolved, flew Apollo 15, 16, and 17. I put this in mostly just because I love the picture. That's taken from a distance of about 3 miles. Jack Schmitt and Gene Cernan, using the lunar buggy, the lunar rover, got as far as 7 kilometers away from the limb and out of sight of it. Their ride back, which to me is about as far out on a limb as human beings have ever gone. In the years that followed, I continued with the working with spaceflight. There's a system running on the space station right now called Timeliner, which is a sequencing language that sort of replaces, for operations that have become mature, it replaces the action of the men with a programmable system using something close enough to natural language that the actual operational troops can create those programs. It's built around a language which has constructs like when, whenever, before, after, and so on, and the ability to make decisions based on the full range of data that's available. And I did leave the space business in 1998, and among other things, became an artist. That's the lower picture. I think the introduction said something about geometrical objects. That's a pyramid that I created, which is floating right now, if you're in Boston, in a body of water called the Fort Point Channel. And just last year, I was finally able to complete and put out my memoir, Sunburst and Luminary, which was a self-imposed requirement, but I knew I was a decent writer. I was in a position to write this story, and I finally got it out. The paperback has recently come out, and you can meet with me if you have questions or want to discuss anything in the exhibition room after this, and there will be copies of that for sale if you're interested. Now, you practice as coders a very powerful art. You play an amplified part in history. It matters what you do. The world has come to know that. Nerdy is sexy. At the place I was lucky to find myself in the 1960s, within the Athenian culture that Doc Draper had created at MIT, where managers hid the organization charts, both from Doc, who ran the whole thing, who didn't really believe in them, and from us at the lower level, who perhaps didn't need to know that either. Within that system, we coders were empowered to take the initiative. NASA didn't quite know what to make of us, so they, to some extent, left us alone to pursue our own methods. Flight software was a wide open field. A junior engineer like me could actually work directly with Apollo astronauts to develop ways of improving their ability to land, which I did with the astronaut John Young. I implemented an offline version which we were able to fly in the simulator that would have let him land the limb in a hat box. It was never approved for flight. It was too radical a change to the software, but it did advance the state of the art. It was a great thing that we had that period after Apollo 11 that we could do that. It was sort of a luxury. I think some of the freedom we had then still operates today. Coding is still mysterious to many people, including perhaps to some of the managers who find themselves in a position of managing coders, but may not understand the art itself. And with that freedom, or that comes from that impenetrability, comes a responsibility, I think, a responsibility to consider more than just the immediate utility, the profitability, if you will, of the code, but also to consider its meaning, not just its utility, but its ultimate nobility, if you will, in the larger or smaller way of what you're doing, its standing in human history, its relevance, its legacy. And that's what I think coders should keep in mind, that they are in that position of having more power to consider that than perhaps they would have realized they had. Thank you very much.